Okay,
cool.
Yeah.
Now,
Okay.
I'm not sharing anymore, right? Or
You are sharing now. Yeah, your screen is on.
my screen is on? Okay.
Yeah, so that's fine. You don't need to
But it's
change
okay. I think it's okay. This is good and a wonderful view. And just my presentation will be around 4 minutes or something like that, 4 or 5 minutes maximum. And just I will pass you the audience.
Okay, that's very good. Thank you.
Switch off camera, so
Yeah.
I'm still here, but you won't
Yeah,
see me.
and always my viewpoint is always lecture are fundamentally for enjoying science. So please feel relaxed and just in a very friendly atmosphere. So wonderful.
Okay, thank you very much.
So let's start then.
Yeah, okay.
That's fine with me.
Okay, so
1 moment. Now it's
okay.
starting. That's starting. Okay, and you see.
So good evening, good afternoon. I don't know, it's so dark in Spain at this time, but for everybody attending this meeting, it's a great pleasure to introduce to Professor Stephen de Feyter, to the great audience gathered for this seminar. Let me first of all to thank you for accepting our invitation, Stephen, to be one of the speakers of the recently created seminar series, Frontiers in Nanoscience, which hopefully will become an appealing forum for scientific discussions along the next coming years, mostly involving those topics related with nanoscience and with the participation of leading scientists all over the world. Well, let me go to Professor de Feyter, who developed his formation in chemistry as well as most of his scientific career at the Catholic University of Leuven in Belgium, and from his former studies in chemistry, where he got the licentiate degree in chemical sciences in 1993 to the PhD studies under supervision of Professor De Schrijver, working on the topic. This was the title of his thesis dissertation, was a visualization of ordering, chirality, and reactivity on a molecular scale with scanning tunneling microscopy, obtaining the doctorate degree in 1997. He became a postdoctoral research fellow and Fulbright fellow at the California Institute of Technology, well known as Caltech, in Pasadena, in the group of the late Professor Ahmed Chevail, who was recently passed away in 2016, and who was the Nobel Prize in Chemistry in 1999 by the development of femtochemistry. Professor Chevail was a friend of Spain by several collaborations with a variety of Spanish scientists. For the next decade, Professor de Feyter was a postdoctoral fellow research foundation in Flanders. And since then, his career moved very, very fast indeed, getting a position as professor in 2008 and full professor in 2011. Immediately, he became the chair of the Department of Chemistry till 2016. Stephen has been visiting professor at Osaka University, and he served as associate editor of chemical communication since 2010, and still he is. As aforementioned, he is a full professor at the Division of Molecular Imaging and Photonics at the Department of Chemistry since 2011. Let me tell you about his scientific interests, which are mostly nanochemistry and supramolecular chemistry on surfaces. In particular, self-assembly on surfaces is a central topic of his research, with a focus on the relationship between structure and function. His research activities extend to other related topics, namely two-dimensional crystal engineering, templating, dynamics, and reactivity. The ultimate goal in these studies has the ambition to control and tune substrates' properties, as well as to create a platform for the synthesis of new materials, such as 2D polymers. More recently, his group has undertaken a research in the spatially controlled covalent functionalization of 2D materials. According to his own words, the liquid-solid interface is our preferred environment. Thus, his group is very much involved in scanning probe microscopy techniques such as atomic force microscopy, AFM, and also scanning tunneling microscopy, STM, to probe the structural, dynamic, and electronic properties of the functionalized surfaces. As you can see, well-known and utilized techniques also in our institute at India Nanoscience. Just let me to conclude pointing out that Professor De Feyter is the recipient of a variety of important awards and grants. The last one I had in my list is the Lavoisier Lectures by the Université Paris-Diderot. And also recently he was elected member of the European Academy of Sciences. He has also lectureships, the Yoshida Lectureship, which is promoted by the International Organic Chemistry Foundation. And he has been elected member of the Royal Flemish Academy of Belgium for Science and Arts, of course, in the natural science aspect. Let me just say that as a proof of the impact of his research is that he was also in 2013 the recipient of a European Research Council Advanced Grant entitled, well, Nanographolcy. Now it is time for enjoying with his lecture for today, which is entitled Frontiers in Nanochemistry on Surface. Let me just, before concluding, tell you that discussion will be conducted by Dr. Emilio Pérez and will be at the end of the presentation by using the easy to handle raise hand method. So dear Stephen, the audience is yours. It's a great pleasure to have you and here with us virtually in Madrid. Okay, please go ahead.
Okay, thank you very much, Professor Martín. Thank you very much, Nazario. You can see my screen? Yes. Okay. So I would like to take you on a journey where molecules play an important role on surfaces. Before doing so, let me though also mention that I'm associate editor from ChemCom. So I suppose it's a journal you all know very well, and please consider also ChemCom for your next excellent research. Well, I will actually focus on the molecular approach to functionalize surfaces. Now, obviously, none of the things I'm going to show you I've done myself. It's a little bit weird to be here in front of you, be it virtually, to talk about the results, but I'm very proud to do so because all of the things I'm going to talk about is the result of a great effort of many co-workers, some of which who you see here in this picture. I'm also quite fortunate to collaborate with groups worldwide, organic chemists, theoretical chemists, and it's always have been a great pleasure to work with them. I'm a chemist myself, but I like to work with other chemists, obviously, but also with physicists, also with biologists, and I will highlight some of those interactions. We are modifying surfaces, using molecules to modify surfaces, and we try to do so in a nanostructured fashion. Why? Why do we like to nanostructure surfaces with molecules? Well, there are good reasons for doing so. One of the reasons is that we want to have control on the properties and of the functionality. And properties can be reactivity, catalysis, doping, sensing, a variety of properties. Now, we believe that some additional impact on properties can be achieved by indeed nanostructuring surfaces. And this impact can then lead to interesting phenomena at the level of the molecular network, but also at the level of the substrate the molecules are in contact with. And I will discuss with you these different approaches. Now, of course, there are many substrates you can use as a platform or to functionalize with molecules. Now, I will focus on one particular kind of substrate. These are carbon-based substrates like graphite and graphene. There are a number of technical reasons why these are interesting substrates for the visualization techniques I'm going to use. But they have also interesting chemical properties, really supporting the sometimes crystallization of molecules on the substrate. And though they are not really very reactive substrates, I will show you that they can also undergo covalent chemistry and that you can control this in a nanostructured fashion. To functionalize surfaces, we basically follow two strategies. First will be the bottom-up approach, where we rely on the weak interaction of molecules with substrates, so physisorption, as well as covalent interactions of molecules with the substrate, so chemisorption, covalent grafting. But we will also combine these bottom-up approaches with top-down approaches, where we will use tools basically at the nanoscale to additionally structure our surfaces at the desired length scale. So let me first start with the bottom-up approach. Now, and among the bottom-up approaches that we're going to use, physisorption and self-assembly gonna be the, well, most important one. So what is self-assembly? I think many of you know this. It's a, let's say, a nature-driven process, a spontaneous process in which particles, in my case molecules, can spontaneously organize, and in our case, they organize on surfaces. And this is shown here in this small movie where molecules basically, they come from, can be the UHV conditions, can be a liquid, they arrive on a substrate, they are dynamic, yeah, and based upon molecule substrate and molecule interactions, they can create, yeah, highly ordered patterns. In doing so, they nanostructure the surface. It's a very simple approach. You do not need an operator to force the molecules to do what they do. It all goes spontaneously. And a thing to stress is that our research area is indeed, or research environment is the liquid-solid interface. So we bring our molecules from a liquid environment in touch with the substrate. And whatever phenomena I'm going to discuss with you, it all happens at the interface between the liquid and the substrate. Of course, we are eager to see what we are doing. And there are a number of tools that you can use. And if you are looking at molecule substrate interactions, scanning probe microscopy tools are actually pretty useful in doing so. And the one technique I am going to focus on today is the use of scanning tunneling microscopy, which works quite well on conductive substrates, to visualize the molecular structures, supramolecular structures formed on the surface. And I suppose many of you know about scanning tunneling microscopy, but it's a technique where basically a tip rasters or moves over a surface, and by applying a voltage between the tip and the substrate, a tunneling current is induced, and this tunneling current will depend on the distance between the tip and the substrate, or can also depend on the nature of the molecule in between the tip and the substrate. And this will lead to an XY coordinate dependent change in the absolute height of the STM tip, which is then translated into a color scale and a gray scale. And that often leads to pictures that we kind of associate with molecules or with molecular organization. Let me give you a first example of this self-assembly approach at the liquid-solid interface. And I start with a rather complex or challenging example. Imagine you take 4 different molecules, not related to each other, and you bring them on a surface from a liquid. How are they going to behave? Will they phase separate? Will they co-crystallize? So based upon a number of years of experience, we actually designed, and this is my group, but also the group of Professor Yoshito Tobe at Osaka University, we designed a system by selecting 4 molecules, the 4 molecules you see over here, and we designed them, selected them in a way that we predicted, or basically at first stage hoped for, that they would form the type of network that you see over here, where you have a coronine molecule, this type molecule, here shown with this yellow disk, that it would be surrounded with 6 of what we call this shell 1 molecules. The shell is shown over here, yeah, and by adding then the shell 2 and shell 3 molecules, that we would continuously build larger shells around the initial structures to end up with this kind of morphology or architecture here at the right-hand side. But let me explain it to you by showing images. Now, it's important to say that of these 4 components, if you bring them by themselves, just as a monocomponent on the surface, none of them will actually form a structure that relates to the targeted structure over here. So if you would just take this shell 1 molecule, it would form by a model this kind of network on the surface supported by hydrogen bonding. However, if you add coronine to this shell 1 molecule, this kind of, and here I show it or indicate it with the model, this kind of motif is formed where you have a coronine molecule surrounded with 6 of the isophthalic acid molecules. If you then make a mixture of the coronine, the shell 1 molecule, and the shell 2 molecule, well, this mixture leads to a 3-component network. I show it here in the cartoon. You have the coronine molecule surrounded by 6 isophthalic acid molecules, so the shell 1 molecules, and then surrounded by 6 of these shell 2 molecules. And indeed, also in these STM images, you can recognize that. Actually, STM is a rather, you could say, simple visualization technique, given that you used appropriate molecular systems. You can clearly see here the bright coronine molecule surrounded by 6 of these shell 1 molecules, surrounded by 6 of these shell 2 molecules. The triangle features over here, these are the triangle cores of these shell 2 molecules, and these long features over here, they are the alkyl chains. So indeed, if we then make a mixture of the coronine, the shell 1, shell 2, and shell 3 molecule, finally we end up with this kind of, I would say, rather beautiful feature, beautiful structure, in which indeed we realize the formation of this kind of multi-component network. There is, of course, an aspect of beauty in it, but there is also an aspect of science in it. Science, because by doing so, and I don't give you all the details here, we learn quite a bit about the thermodynamics involved, but also about the kinetics and kinetic traps that can actually play a role in the successful formation of this kind of networks. Yeah? And all of this, again, I repeat, is simply achieved by mixing these 4 different molecules in very well-chosen concentrations in an appropriate solvent and bringing such a solution at the liquid-solid interface. And this is only one of the many systems we and others have investigated. And what we have learned is that by controlling solvent, concentration, substrate, temperature, sometimes the thermal history of the sample, that we can have some control, or quite good control even, on the organization of the systems, of these molecular systems on the surfaces. Such systems we call self-assembled molecular networks. Now, of course, you will probably think, well, beauty, that's nice, but what about function? Well, the system I have introduced you, the 4-component system, is not functional at all. It just serves some fundamental science, curiosity-driven questions. Nothing wrong with that, of course, but we would like also to go to some more functionality. And first step in functionality in the framework of what I'm talking about is to add a stimulus to your system. A stimulus such as an electric field, light, temperature, solution flow, surface potential. Can you use such an external stimulus to have an impact on the, well, first of all, the organization of your system on the surface? And I will just highlight one example, which is the impact of the electric field at the liquid-solid interface. Of course, we have an electric field because we apply a voltage, yeah, on our STM tip. And there is a voltage difference between the tip and the substrate. Well, first of all, you have the size of the electric field, but you have also the polarity of the electric field. You can bias your tip positive, or you can bias your tip negative. So if you bias your tip positive, electrons tunnel from the substrate towards the tip. If you bias your tip negative, electrons tunnel from the tip towards the substrate. Now for this system here, yeah, that has an impact. Under conditions where the substrate is positively biased, we get a porous network, as shown over here, where each of these small triangles is actually one such molecule. So they form a porous honeycomb type network sustained by hydrogen bonding. If we now switch the polarity though, we get a high density network. All of that is on HOPG, graphite, using octanoic acid as solvent. Now, what about functionality? Well, you could consider this as a responsive system where you can open and close the pores of such a monolayer, one molecule thin network at the liquid-solid interface. And indeed, by changing the bias, yeah, we can go from a high density, so non-porous, to porous network, high density, and porous network. Yeah, of course, limited functionality so far, but it becomes more interesting when we consider that in the pores, in these supramolecular pores, we can actually trap other molecules, other species, such as chlorine in this case, or a more complicated molecule in this case. Now, the details do not matter too much for the moment. The point I want to make is that indeed now, starting from a situation where the so-called guest molecules are trapped into the porous network, that by changing the polarity, that we can go from the porous network with the guests to the non-porous network, meaning that the guests have been expelled from the network. And that's a first kind of functionality at the level of these supramolecular networks. Now, another example, an iterated molecule, is this one here, but which actually carries a reactive group, a chemical reactive group. This is boronic acid. And the other example, it was just a carboxylic acid group. Now, by itself, this molecule forms under positive sample bias conditions, forms this type of network. Okay, you see it over here. So these are, of course, the scales. So this is a high resolution image or a zoom of it. This is just one molecule, and it forms a self-assembled network. But it actually came to us as a quite pleasant and unexpected, of course, surprise that when we change the sample bias from positive to negative, that something else happens. Namely, we get a different structure, but a different structure which is not supramolecular in nature, but which is covalent in nature. By changing the bias polarity, we can actually, at room temperature and locally, induce a reaction where we create these boroxene groups and form what we call two-dimensional surface-supported covalent organic frameworks. And it's pretty cool that we can do so, because by using the STM, we can actually use it as a trigger to start locally the reaction. And therefore, it can also allow us to follow the reaction process in real time. This is then the same molecular system where we start from the self-assembled molecular network and where we change then the bias to negative bias. And in time, we see that the original self-assembled molecular network, supramolecular network, disappears and is replaced by the covalent, so organic framework. And we can follow this, of course, more in a quantitative fashion as a function of time. And we can even look into details of this process, starting again from this supramolecular network. Again, this is one molecule here. You see the triangle, and then you see that as a function of time, these covalent organic frameworks, porous units are being formed. So STM gives us actually a close-up view of how a pre-organized molecular self-assembled system can be converted into a covalent organic framework. Also, the opposite is possible. We can start from the covalent organic framework and induce a depolymerization reaction simply by reversing the bias. Instead of having a negative sample bias, if we go to positive sample bias, we go from the 2D covalent organic framework over here to the self-assembled molecular network over there. So we have control as well on the polymerization as well as on the depolymerization. And of course, what is the mechanism of this? And it's something that we're still working on, actually. But there are a few questions that one could ask them ourselves. I mean, is just the electric field by itself enough to induce this phenomenon? Well, some control experiments learn us that it does not work at the air-solid interface. So if you would have removed all solvent and you try to polymerize or depolymerize, it doesn't work. You need a solvent such as octanoic acid. Indeed, if we added octanoic acid to a dry film and then do the bias switching, then we can induce again these dynamics. I think that's rather maybe powerful also approach to investigate chemical reactions on surfaces to depolymerization reactions. This is one of the things we are doing right now. And recent example is that we have not only looked at monocomponent systems, but that we also started to look at multi-component systems as far as 2D COF formation is concerned. Again, based on the control of the STM-related electric field that we can apply. So, and that system is shown over here. Again, we use this boronic acid, but then we also add this molecule, and it's known that these two monomers can give rise to a different covalent organic framework, as shown here. And these are images of the monomer. Yeah, this unit, this HHTP, we cannot visualize by itself. Yeah, but this is the monomer I have introduced it before, and this is after the polymerization. And I think the interesting aspect here of this approach was that we could, by playing with the electric field, that we could go from one stage to another stage. So starting from the monomer self-assembly to the 2D covalent organic framework, yeah, the monocomponent 2D covalent organic framework of the boronic acid, the one I have shown you before, but by then applying the electric field, that we could go to the bicomponent covalent organic framework, and we could as well induce or realize the polymerization as well as the depolymerization of this process. So we call this dynamic network switching because we can convert one covalent organic framework into another covalent organic framework. Again, these frameworks are only one molecule thick, and they are supported by a graphite substrate. And we have basically followed this transition in time, where we first start, for instance, so the green hexagons over here are this COF1, so of the monocomponent, and the blue triangles are the two-component COFs. And you see that as a function of time, indeed, we can induce more and more of the two-component covalent organic framework. It also allows us, if we zoom in a bit, it also gives us some insight into how the process works, in the sense that we can see how from the self-assembled monolayer, we actually form the 2D COF structure, the 2D COF bicomponent structure, or when starting from the monocomponent 2D COF, how this monocomponent 2D COF, which has a pore which is smaller than the bicomponent 2D COF, so how the monocomponent 2D COF is converted into the 2D or bicomponent 2D COF. So as we think that still a lot is to learn from this when we really look into the quantitative aspects of this, but at least so far, as a kind of a proof of concept, we have established that it is possible to follow this kind of reactions. And we have also, or we are also looking at different types of 2D covalent organic frameworks, such as the one shown over here. And just to mention or to remind you that all of this is recorded with scanning tunneling microscopy at the liquid solid interface, at room temperature. And despite all of that, we can achieve pretty nice resolution. Going to a bit more applications. Of course, I have talked about 2D, but what about 3D? Are we really limited to one molecule thin layers? And is there anything to achieve if we go to 3D? Well, as one example, I would like to introduce this one. This is a collaboration with a group of Professor Meyer at Eindhoven University. And one day they came to us with these molecules. And they were wondering if we would be able to visualize these molecules, their self-organization at the liquid-solid interface by using scanning tunneling microscopy. And this was rather challenging question to us because we know that these dimethyl siloxane units, they don't like to interact with graphite. In contrast to alkyl chains, they like to interact with graphite, but not these dimethyl siloxane groups. So guess what will be the difference if you look at these three molecules? There is none. There is no difference in the STM images. They all seem to form this kind of honeycomb type lattice, and the bright areas, they refer to where the naphthalene diimide units are adsorbed. But if you look at the unit cells for all of these compounds, this is the same. How can we understand this? Well, the only solution to this issue is assuming that the dimethyl siloxane units are actually not adsorbed on the surface, but are expelled into the liquid phase. Because the footprint of these molecules, of these materials on the substrate is dominated by the interactions, the non-covalent interactions between these naphthalene diimide units. Of course, these molecules differ in the length of the dimethyl siloxane groups. And indeed, if we then look with contact angle measurements, then we also observe this, that of course, the molecules with the longest dimethyl siloxane groups, they show the highest contact angle. So this is the first type of, you could say, application. But so far, I have only touched about properties at the level of the molecular network, non-covalent as well as covalent. But what about the substrate? Well, actually, you can use these self-assembled molecular networks to introduce or change the properties of the substrate. And I would like to illustrate this with an example of doping. So we use quite often graphite as our support for investigation with scanning tunneling microscopy, the formation and the characteristics of the self-assembled molecular networks. But you can, of course, use graphene. Of course, graphene and graphite, they differ quite a bit in their properties. And I do not, or I will not discuss in detail the properties of graphene, this Nobel Prize winning material, but it is possible using self-assembled molecular or molecules that weakly interact with graphene actually to dope graphene. And we were absolutely not the first to do so. I mean, quite some years ago, the group of they illustrated that if you bring these molecules in contact with the graphene substrate, that actually you can dope graphene. But we thought a bit differently. We thought differently in the sense that in order to have the best possible control, you actually need to have control of the density of the doping groups in contact with the graphene substrate. Given that, for instance, an amine functionality, can act as a doping unit to create N-doping on the surface. Well, an obvious, from our perspective, approach to control the density of amino groups on the substrate is, well, by having them organizing on the substrate in the form of a self-assembled molecular network. So we took a short alkyl chain and a long alkyl chain amine and exposed that to the substrate. Now, this is what we hoped would form in terms of the molecular organization. And of course, the long molecule should have a lower density of amino groups on the surface than the short molecule. Well, we can use STM, AFM to visualize the structure that these linear molecules form on the substrate. And indeed, they form this kind of, I would say, from our perspective, straightforward self-assembled molecular networks where they organize in rows. But then we teamed up with our colleagues at IMEC, which is a Nanoelectronics Institute in Leuven, and we looked into the impact of exposing graphene field effect transistors to a monolayer or even multi-layers of this type of molecules. And it was pleasing actually to see that the impact, basically the transfer curves that you see, and basically the degree of doping that we then can extract from this data, that the degree of doping scales very well with the density of the amino groups that we have on the surface. Actually, we can restore the properties of the graphene, of the pristine graphene, by just washing away these molecular physisorped systems. Okay, let me now move to second part of as far as the type of molecular interaction with the substrate is concerned. Let me move on to chemisorption. Physisorption is great, but it's always gonna be relatively weak, the interaction of the physisorped molecules with the substrate. Now, we were actually quite intrigued by this study of the groups of Jean-Michel Savian and Jean Pinson many years ago in '92, where they introduced the use of diazonium salts, diazonium salts to basically covalently graft to different types of materials, including graphite. So we took this type of molecule, amino, modified it into a diazonium, and then activated it electrochemically to create a radical in the hope that we would form this type of, well, covalent structures on the surface. I mean, we were quite positive that it would happen. And I think our contribution to this area has been that we have used scanning probe microscopy really to look, what is formed on the surface. And with STM, for instance, each of these individual bright blobs is an individual molecule covalently graphed to the substrate. And you can see that we can tune the density of these covalently grafted molecules on the substrate. Of course, it was known before that you can tune the density by controlling the electrochemistry, but now we could visualize that with scanning tunneling microscopy. Actually, in some cases, we have quite good spatial resolution where we can actually have intramolecular resolution here, basically visualizing the tertiary butyl groups on the phenyl unit. Of course, there is still the question, do you really have a covalent attachment on the substrate? And we believe we have, because by using a Raman spectroscopy is very sensitive technique to establish any type of defect introduction in graphite as well as in graphene. And particularly the D band here is typically accepted as be a good marker of the formation of a covalent bond. And by visualizing or doing these Raman experiments, we could indeed establish that as a function of concentration, for instance, indeed, we have more and more of these covalently grafted molecules. I will now talk about something that we did more recently, in the sense that all of this was electrochemically done, but there are also good reasons to try to create these radicals in a chemical and by chemical reduction. And recently we showed that some iodide chemistry can be used, or that ascorbic acids can be used to activate the diazonium salts towards the formation of the aryl radicals, or actually also other systems, not diazonium, but also iodonium salts can be used to create highly density grafted systems. Okay, so we can graft molecules on a surface, and in particular, we can use scanning tunneling microscopy to visualize what we have on the surface. As an application, still something that we are working on, we hoped that we could use the grafting of molecules on a covalent substrate to promote, for instance, the quality of an ALD layer. If you normally try to grow an aluminum oxide layer by an ALD process on graphite or on graphene, the quality is often not very good. And we reasoned that if we would graft this kind of molecules on the substrate, that they could basically promote the interaction with the aluminum oxide, and therefore provide a good platform for good quality aluminum oxide layer. Schematically, it's shown over here, where we create aluminum oxide on top of the a functionalized substrate. Now you could argue, well, that's nice, but yeah, you do not have aluminum oxide on graphite or on graphene. You have it, well, on top of a bridge layer. Well, the good news is actually that we can remove this bridge layer just by heating. At least we can break the bond between the covalently linked molecules and the graphite or graphene substrate. Let me move on to another, maybe curiosity-driven application. Given that you have a substrate, a 2D material, can you protect that 2D material from active, reactive impurities or reagents in your solution or in your environment? And we reasoned that covering in a monolayer fashion the graphite by long chain alkanes, that, because they form a high density network on the surface, that could do the job. And indeed, so this is a self-assembled monolayer of a long alkyl chain on graphite. This is one molecule here, and they stack in rows, these molecules. If we now expose such a layer to the radicals that we can generate, for instance, electrochemically. This is the radicals that I have talked to you about. The question is, if you have just one layer of these alkanes, and the alkanes are lying flat on the substrate, not orthogonal, they're lying flat, will this be enough to protect the substrate? From radical attack? And actually it does. This is the covered area, so an alkane covered area of the carbon substrate. This is a non-covered area, and you clearly see the difference in and density basically of the grafted molecules. But it's not perfect. And why is it not perfect? Well, these areas are graft free, but these bright areas, these are areas where you have grafted molecules, and they follow this kind of lines. Why this kind of lines? This is because these alkane molecules, they form polycrystalline domains on the surface. And at domain boundaries, where you have one crystal, monolayer crystal of the alkane, at the boundary between two of these alkane 2D crystals, you have a defect, basically, because there is a not perfect coverage of the substrate. And in those defects, the radicals can attack. Now, we thought maybe that's actually a good thing, because if we try to tune this in a rather clever way, or by just being lucky maybe, and we might actually have an additional control to also now nanostructure the covalent grafting on the substrate. And actually we reasoned that maybe the most weak spot, if you have an alkane layer, is the space, very small space between two of these rows. This should be the most, if reacted, it should be the most reactive area. And indeed, we succeeded in that, in tuning the reaction conditions in a way that the radicals attacked the surface, but only in between rows of these alkane chains. And here you see SDM images that support my claim, where we have used alkanes of different length. Yeah? And all these bright dots here are individual grafted molecules, and you can, I think, clearly see the row type structure which is formed, and this is due to the templating effect of the alkanes. Well, you can also use a porous network to introduce the same type of templating, yeah? Where now the radicals are expected only to attack the graphite surface in the porous areas. And here you see indeed what we could realize recently. And you see it nicely here at the right-hand side, where we have a hexagonal template as shown in this cartoon. You see by the organization or the appearance of the bright dots, and each of these bright dots is such a grafted molecule that indeed it really nicely reflects the honeycomb type lattice formed by the molecular template. So this is control at the nanoscale. We can also try to control at a bit higher scale, at the micro scale. And one of the approaches that we took was to cover the substrate, not with molecules, but with beads that by themselves then formed a self-assembled molecular network. So plastic beads, polystyrene beads. And indeed, if we then expose such a network, here you see an AFM image of this, of a layer of these beads on the surface. If we then expose this type of template to reacting molecules, then we see where the molecules grafted, actually they graft in between these beads. Well, this is a straightforward approach. But sometimes life is full of surprises, and this was another surprise. We could actually almost make the same type of nanostructured, covalently grafted substrate at the micro scale, but just by a bottom-up approach, by mixing two different diazonium salts. Yeah? And by doing that, we observed that under conditions, so only under conditions where we mix two of them, that we create areas which are molecule-free. We call this corals because no molecules are grafted in those areas. And we could actually have control on the diameter and the density of these molecule-free areas by playing with the ratio between those compounds, by playing with their concentration, or by using chronoamperometry instead of voltammetry. Yeah? So all of this led us to the control of the nano microstructuring of the substrate. And we believe that the species responsible for the fact that we have some areas which are not grafted, that this is due to bubbles, gas bubbles that are formed and adsorbed on the surface while we are exposing the substrate to the reactive radicals. Having actually formed these corals, as we call them, you can then start to fill them with molecules. And how do we fill them with molecules? Easy. We now expose this modified surface to a liquid with a molecule of interest. And this molecule over here, it self-assembles in rows inside these corals. Actually, we create some nano containers where we now can investigate the self-assembly, the self-assembled molecular network formation of molecules. So these are all, you could say, individual and independent containers. As this is a reactive molecule, by shining a light on it, actually, we could transfer the molecular organization to a polymeric one. Such a bright line is a polymerization reaction that has happened on the surface. So let me now quickly go to the combination where we use nanolithography. And for the nanolithography, the bottom down approach, or the top down approach, sorry, what we do is the following. We have already our chemically modified surface. So you know these real radicals have covalently formed a bond with the substrate. But actually we can use the STM tip to locally remove them by bringing the STM tip closer to the substrate. And actually, we can start to write. So all these bright dots here are covalently linked molecules to the substrate. And these letters are areas where we have removed these covalently grafted molecules using the STM tip. We can start to write. You can create areas of a given size and shape. Yeah, we have full control on that. And of interest is that actually, if you remove or if you do this nanolithography in the areas where we have nanoshaved using the STM tip, where we have removed the molecules, at least that's what we claim, yeah, that actually if we look in such an area with Raman spectroscopy, that indeed this D band, which is typical for a covalent functionalization, has completely disappeared. So we believe indeed that by this lithography approach, we can locally regenerate graphite or regenerate graphene, so creating the sp2 bonds. Now, we took this as a challenge to investigate what would happen now if we put molecules in this kind of corals, which we have made ourselves of a given size and shape. So this is the process I have already explained. We remove locally molecules from the surface, yeah, and then we expose that modified surface with the liquid which contains the molecules of interest. This process we call the dry shaving approach. Well, the PhD student who did all of this was pretty excited initially, but he turned, well, quite disappointed also quite quickly, because these are domains of that molecule that I had introduced you before into a square coral. Yeah, and you see different domains, but if you compare this with graphite, which happened on pristine graphite, there is almost no difference. So there seems to be no effect of the confinement, because we had hoped by basically putting molecules in small 2D containers, yeah, that would affect their self-assembly properties. Now, fed up with this, and actually to do experiment faster, the student decided actually to do the shaving already when we had liquid phase on top of the modified substrate. What could be the difference? We call this the wet shaving approach. Well, so this is shown over here, right? Well, the difference is huge. Instead of one domain, now actually, or instead of many domains, now actually such a coral is filled with only one domain. Yeah, right? And moreover, that's the same over here. So these letters actually contain the same molecules. You see these rows of molecules. Yeah? We have, this is our collaborator in Japan, Professor Tobe. We also filled the letters of his name with these molecules. And what was quite special is that all these molecules organize in the same direction. Because of the symmetry of graphite, there should be rows like this, or rows like that, or rows like this, but this does not happen. It all happens in the same direction. We have here an alignment effect. And we think that we have this alignment effect because of the following. Yeah? If you look here at these square shaped systems, the molecules faithfully align along what we call the slow nanoshaving direction. So the tip moves like this, fast, and goes slow from top to bottom. So the rows align along the slow direction. And that is okay for square, disc-like, and also triangular corals. Except if we have a triangular coral where we shave from the apex to the bottom. Then if you look into the statistics, then we see that there is now a large deviation from the alignment from top to bottom. Why is this? This is because we affect nucleation. Imagine you start the shaving and you start it in from the apex of the triangle to the bottom. Well, if you look at the zoomed out area, a molecule, when it starts to self-assemble at the nucleation step, it can adopt basically 3 different orientations. If, however, you shave from the apex to the tip, well, you you create an anisotropic shape, and these long alkyl chain molecules will probably intend to align preferentially along that direction. So we believe actually by playing with the shapes, with the speed of shaving, etc., that we will be able to investigate nucleation phenomena at the liquid-solid interface. Now I'm coming closely to the end of my presentation. I just would like you to show some what I find quite, well, pleasing examples of indeed now how shape, coral shape, can have an impact on the confinement, on the self-assembly of molecules. This is the long alkyl chains I have talked about before. And if you have a rectangular type molecule shape, the molecules align in nice rows. If you have this kind of banana type corals, you see that these molecules, well, the organization of these molecules is frustrated by the shape of the container. Yeah? And we can all look at that at the nanoscale. So we have now applied this. Apply this, for instance, for polymorph selection, where we have shown that this is a molecule that can self-assemble into a porous network and to a high density network. We have shown that you can actually modify the appearance, not the appearance, but the polymorph appearance actually inside these corals by playing with the size of the corals. Yeah? And in this particular system, the non-porous high density phase is preferentially formed in the smaller, smaller corals, while if you go to the higher or larger corals, actually the non-porous phase gets promoted. I don't have time anymore, but we have also, in addition to polymorph selection based upon the size of the corals, we also have looked into the impact of the orientation of these corals with respect to the symmetry axis of graphite. And we can also selectively absorb one of the polymorphs of this compound depending on the orientation of the coral with respect to the symmetry axis of the graphite substrate underneath. And something which we've done recently is actually from a racemic mixture, so containing 2 enantiomers of a molecule, selectively adsorb one of the enantiomers in one coral, depending on the orientation of the coral with respect to the symmetry axis of the graphite substrate underneath. I admit this is rather fundamental in terms of the approach, but at least it learns us quite a bit about, it gives us a tool actually to even investigate more in detail self-assembly phenomena on surfaces. And by mentioning that we can also now look at reactions inside these corals, basically 1,2 polymerization and also 2D polymerization, I believe I have given you enough examples of, let's say, the power of combining bottom-up and top-down approaches to functionalize surfaces in order to create new properties and new functionalities at the level both of the substrate as well as of the patterns, molecular patterns or structures formed on the substrate. And with this, I would like to thank you for your attention.
Thank you very much, Professor De Feyter. Thanks, first of all, for accepting our invitation. We knew it was a good choice to have you here, but now after your talk, I think it's obvious to everyone. It's amazing what you can do with molecules on a surface. You controlling the supramolecular chemistry, controlling the covalent chemistry, controlling them to do something else that the other molecules might want to do. And I think we've all, I'm sure we've all enjoyed it very much. So with this, we open the question session. You should have a button at the bottom of your screen that says raise hand. If you raise your hand, I'll be able to connect your microphone. And if you don't want to talk or can't because you don't have a microphone, you can also use the chat and I will just read out the question. So On you go. Any questions for Professor De Feyter? Shall I break the ice? So obviously, I think one of the most beautiful aspects of your talk is like the degree to which you control a relatively large surface. So you know how like typically physicists, when they play with controlling an atom at a time and things like this, you instead control like a relatively large surface. But my question is, especially with coughs and things like this that might have applications, how large are really these surfaces? I mean, what is the throughput that you could get out of this kind of assemblies?
Yeah, I think there are two aspects in that. First is probably what is the coverage on a substrate, and I would say if it's based upon self-assembly or even the other approach, I would say, of course, we only look at a small area with STM, but the full surface is functionalized. And another aspect, though, and probably even more important, is the aspect of well, let's say crystallites, 2D crystallites. If you refer, for instance, to the self-assembled molecular networks, how big is a domain basically, or how big or how large is the area of molecules that are organized in the same way? And that will depend from system to system. You can play with concentration, you can play with the solvent and so on. But in particularly, I think it becomes important when you look at covalent organic frameworks. Yeah? Because I did not talk about the quality of them. I only showed that you can use STM locally to investigate them. Now, of course, for many applications, you want to have high quality networks, even high quality covalent organic frameworks. And though most of the, I think, or that many of the systems reported at this stage are, I would say, at the sub-micrometer level in terms of the domain size, or call it the particle size of such a 2D covalent organic framework, I think we have now hit a way basically to make them micrometer, if not millimeter size, in monocrystalline, basically, on a substrate. So we are working on that. Of course, the quality of the substrate also have an impact on the quality of what you form on top of that. But it is possible. It is possible to move forward and to go to, let's say, high quality functionalized surfaces. I have focused, of course, also on solid substrates. I mean, that the ones that can use and are with imaging tools like AFM or STM. On the other hand, you can also think of to upscale, yeah, to implement what we have here investigated at the liquid solid interface with scanning with microscopy techniques, but basically also to apply that to well, do solution-based chemistry where you have graphene flakes and solution and so on.
Cool. So we have a couple of questions. One is on the chat, and it's related to what we were speaking about. So Jorge Lobo asks, in the case of reversible coughs, can you play with the potential or other parameter in order to improve the order of the assembly to make it more extensive?
Yes, we can play with that, but note that what we do so far, I mean, when we work with the electric field, that this is a local phenomenon. Yeah? So where we initiate the reaction, the polymerization or the depolymerization, that happens under the STM tip. And of course, we could do so in combination with scanning to, on the local scale, improve the quality. But I think on the long run, this is not what you want to achieve in terms of an application. So yes, we can improve the quality of the 2D coughs using our approach, but only locally so far. Of course, we are curious ourselves if we can develop the strategy that we have developed also to do large area synthesis, controlled synthesis, high quality synthesis of these on-surface covalent organic frameworks.
All right, so we have another question from Sebastian Grija. says, thank you for the great talk. I wonder whether it is possible, or at least hypothetically possible, to remove already formed supramolecular structures from the substrate surfaces without destroying the structure, sort of like a supramolecular printer.
I would say that the likelihood of being successful in doing that is very low, because most of these supramolecular structures networks are formed because they are supported by a surface. Yeah, if you remove the surface, yeah, in many cases the intermolecular interactions will not be strong enough. I mean, given that the system is in a liquid environment and will not be strong enough to keep the structure. We often think in the other way around. Can we use what is already preformed in solution to help us to form actually structures at the liquid solid interface? And in a number of cases we can. We know that we have some, in a number of cases, we know there is some pre-organization in solution, and that is also then transferred in the network, the architecture we form at the liquid solid interface. But the short answer is no. To go from the covalent, non-covalent self-assembled molecular network to keep that in a solution phase is probably not going to work.
Okay. So we have another question from Fabian. And first of all, Fabian, thanks for typing it, because I was trying to activate your microphone, but I couldn't. So it's good that you typed it. Fabian Calleja says, I would like to know what is the importance of the macroscopic shape and material of the STM or AFM tip. Do you have a special procedure to form the tips, or is it not an important factor?
And the type of experiments, as far as the imaging is concerned, we use just a platinum iridium wire, and we just take scissors to cut the tip. So we do not really, of course you can do it electrochemically, but we basically, the experiment or experience told us that for the type of systems that we are looking at, we do not need to take really extreme precautions as far as the sharpness of the tip is concerned, because you know the tunneling is such a local effect, distance dependent effect, that you will basically always have a tunneling current. Of course, that might be different in terms of the need for a good quality tip if you go to another environment, but a liquid solid interface, we just typically just cut our tip with the with scissors. Now, what it is impossible though that the shape of the tip has an impact. And we have seen this when we looked at these alignment phenomena that I have shortly mentioned at the end of my presentation, that when we do the statistics, that the statistics in terms of alignment and so on, that can differ, or that can depend on the specific tip you use. So for a number of phenomena that we observe, the macroscopic shape of the tip is important, but it is not really important for providing us with a high imaging resolution.
So there's another question. So I saw Nazario raising his hand, but we'll leave him for the end, if that's okay with you, Nazario. So we have another question from Si Chao Li, who thanks you also for your fantastic work. And he says he's wondering if there is a water issue for your experiments.
If there is
a water issue, so an issue with humidity, especially for the molecules that have hydroxy in their structures.
In general, yes, there is an issue that we don't want to have too much water into our system, as then other processes than tunneling processes rule basically, or dominate then the current that we measure. We quite sometimes we basically do a distillation of the solvents that we use, and we note though that there is sometimes, if humidity control is not working fine, yeah, that in particular if the humidity of the measurement room is too high, it's really more difficult to create good quality images. So we always try to create an atmosphere with a low humidity. Actually, you can, but you might know this, you can actually even measure in water, using water as a solvent. But to do so, I mean, in combination with using scanning tunneling microscopy, then you need to coat the STM tip with a polymer coating so that only a very small end of the tip, the apex, will interact basically with the substrate and with the surroundings, with the solvent surroundings. So in that way, it's possible to image.
Okay. So we have another question from David Ecija, who also thanks you for the excellent talk, and asks about the role of the substrate temperature, if you have a control over it and if you can tune it.
Yeah, we have done a temperature-dependent experiment. So there is, so was the question related to cleaning or not, or just in general, temperature?
I think in general, what is the role of substrate temperature?
Yeah, so substrate temperature is important. We have looked at phase transitions between, let's say, two polymorphic patterns, and we could control basically the relative ratio of the two phases by temperature control. So because we have a heating stage at the liquid solid interface where we rammed where we also measured that the SDM experiments at the specific temperature, we could go up till 80 degrees. So I mean, the short answer should be it's system dependent, yeah. But quite often we indeed heat the substrate also even initially to avoid kinetic traps, because quite often if you are at room temperature, low temperature, you even at the liquid solid interface where there should be quite some dynamics, and that is something I did not stress, the dynamics, but when molecules are adsorbed on the surface, they can in principle also desorb again from the surface. Although you have this kind of dynamics, which you not have under ultra high vacuum conditions, sometimes kinetics drives the assembly rather than thermodynamics. And to promote basically thermodynamics to win or to compete with kinetics, quite often we start by bringing the solution and the temperature at a higher so the substrate and the solution at a higher temperature in contact with each other, and that often promotes actually good quality formation of these self-assembled molecular networks.
Excellent. So I think there are no more questions from the audience. I think Nazario, it's your turn to ask, and then I think we'll leave it at that after your question, Nazario.
Thank you, Emilio. Well, first of all, congratulations for the wonderful lecture, as everybody agreed, and also by the fascinating and amazing results, certainly. Let me, before my question, start with not a statement, I would say a prediction. It is difficult to predict, I know, talking about future, but I'm pretty sure that self-assembly will be the third Nobel Prize devoted to supramolecular chemistry. I'm pretty sure about this because, of course, there are many views of self-assembly involving COFs, MOFs, but also cages by design, Makoto Fujita, but also this is on surfaces will also contribute. So it's really fantastic. I completely in favor of supporting this idea. Okay, related with my question is that if you are handling the interface in between the liquid and the solid, how do you control chirality on 2D surfaces? Because it is, I understand that chirality on 2D or 2D chirality on surfaces is possible to do it. But as soon as you are handling solvents and solution, how do you control chirality or the final chirality in the systems?
Yeah, this is an aspect I did not really focus on. Chirality in the sense that, of course, let's assume if you have a system, even a prochiral molecule, you know, it can form, as you know, it can form networks which are each other mirror image, right? So, and also if you take a racemic mixture of two enantiomers, if they form a conglomerate on the surface, you will have mirror image, let's say, or enantiomorphous patterns, as we call them, on the surface. So if your question is now how you can select one of them, is your question, does that relate to that, Nazario?
Well, that would be a way of controlling. Yeah, that could be.
So we have shown that it's possible actually to control. You can actually use chiral solvents even as your medium, and we have shown for a couple of systems that in an enantiopure solvent, the molecule of interest, and it was an achiral system or a prochiral system, let's call it like that, that only one-handedness was formed on the surface. So you can work with the nature of the liquids, of the solvent. You can actually also work with making a combination of achiral and enantiomer pure molecules, where the enantiomer pure molecule acts as a sergeant somehow to dictate the network formation of the other one. We have published this in Nature Chemistry a couple of years ago, where we actually, and it was actually, I think from my perspective, quite cool, that we, by just a temperature treatment, we could switch the handedness of the chirality which we had on the surface. That had to do with competitive self-assembly phenomena, etc. But there are a number of tricks, of course, very often system dependent, that you can use to control chirality on the surface. And that's also something which is quite close to our heart, because we see also control of chirality as an additional structural and functional control to materials properties.
Wonderful, fantastic. Okay, congratulations again. Thank you so much, Steve.
Thank you, Nazario.
Very good work. There is one last question. Can we take one more, Stephen?
For me, no problem.
Okay, then let's go for it, because there's just one, so let's just do it. So Juan Leon asks, well, congratulates you on the work, and has a question about the corals, the areas that have no molecules on them. And then it says, you assume that they are formed due to gas air bubbles, but you can control their size and abundance by modifying concentration, if he remembers well. How is this possible? So what is the mechanism behind it?
This is a good question, and we don't know exactly how it works. Of course, it's depend. Well, of course, there's no of course here, but it depends at what. Well, of course, you create, if these are these nitrogen bubbles that are important, you create them at the moment, of course, that you get rid of the nitrogen from the diazonium, and they are probably getting pinned by the substrate because it's up there. Now, why it exactly is that changing the ratio can create, we have some wild ideas there, but while they really have a control then on the diameter, it's still speculative. I must say that we are investigating other systems now. And I can tell you that we found even systems that do not form circular corals, but other shaped corals, and which makes it even more intriguing and complex and challenging to us. But it's one of the things which we are also in collaboration with others, try with other techniques actually also try to get an insight in, to really quantify the amount of gas that is formed, etc., and at what stage, and how it really interacts with the substrate. So let's say at this stage it was rather more phenomenological in terms of how we used it and demonstrated it, rather than that we provided a convincing mechanism in all its details. But I mean, what I'm quite convinced of is that indeed it is though the nitrogen, the gas formation, that is responsible at that point, because we could rule out a number of other alternatives.
Excellent.
Just
So I think
sorry, just to say that Juan Leon is a first PhD, first year PhD student. So great question. Thank you. Go ahead, Emilio. Sorry.
So I was just closing this. So thank you again for accepting our invitation, Professor De Feyter. It's been a pleasure to host you. Definitely, the title of the talk was well justified. It is definitely the frontier of nanochemistry, and besides that, it's an extremely or extraordinarily beautiful presentation to watch. So I think it's been worth it for all of us that are in the evening. And also, I'm sure it was worth it for those that have started the day with your talk. So thank you very much for being with us. And with this, I think we can close the session. I will not turn on the microphones, but I'm sure everyone will love to applaud loudly to your talk. Thank you, Stephen.
Okay, thank you very much for staying with me. Okay, it was a pleasure. Have a
Bye
nice
now.
evening, everyone.
Yeah, bye now.
Okay, bye.
So bye-bye.
Bye.
Bye. Steve? Yeah.
Yeah.
Okay. Gonzalo.
Sí, muy bueno, Nazario, estoy por aquí.
Ah, vale, bueno, ya se ha desconectado Steve.
Sí.
Vale, era solo por habernos despedido de él, pero bueno, está todo, ha ido todo correcto, todo ok, ¿verdad?
Lo he estado viendo yo por aquí, todo bien.
¿Cuántas personas estaban conectadas?
Sí,
No me he
pues hemos
fijado.
llegado a picos de 111, 112 personas aproximadamente. Más o menos la media ha estado sobre 107, que ha sido el
Vale.
rato más estable que ha estado.
Bueno, está muy bien, en torno a 110 personas está muy bien. Vale, pues fenomenal. Oye, pues nada, Gonzalo, muchas gracias, ¿vale?
Perfecto, nada a ti,
Venga,
Nazario.
hasta mañana.
Bueno,
Chao.
hasta luego.